Hello everyone. Today we'll discuss solution related to GATE 2008 manufacturing problem. The first problem is arrange the following process in increasing magnitude of surface roughness of the casting. So different types of castings are given such as investment casting, permanent mold casting, pressure die casting and sand casting. So we need to know the surface roughness. If you see, the surface roughness of investment casting is around 3.2 micrometer. Permanent mold casting, it has got 3.6 micrometer. Pressure die casting, it has got 1.6 micrometer. And sand casting, it has got 25 micrometer. These values I have taken from literature. And what do you mean by surface roughness? Surface roughness is basically unevenness which is present on the surface, which is measured in the terms of RA. RA is nothing but the variation in this height. That is the average variation in this height. Okay. Now, so if you arrange this, then if you see here, the pressure die casting has got the best surface finish. Like whenever there will be less surface roughness, then finish will be higher. So here the first will be R, okay, and second will be P, that is investment casting. Then third one will be permanent mold casting, Q. Then last one will be S. So R has got the best surface finish and S has got the least surface finish. Okay. So which option is valid? RPQS, RPQS. So answer will be this. Okay. Now in the second question, which of the following categories of material is suitable as a filler for brazing of steel sheets? So here steel sheets are given and we have to braze it. Brazing. So what happens in brazing? We take a filler material and we melt it. We melt it and pour it in the gap between these two plates, and due to the mechanism of capillary action, this will go inside of this joint, and after this joining process will take place. So the property which is required is it should have lower melting point. This is the property which is required, and surface tension should be low. Okay, now since here we are brazing steel, so epoxy resin cannot be used as a filler method because where we are brazing, so in brazing mainly metals are involved. Now second is the near eutectic alloys. Near eutectic alloys, and we know that eutectic alloys have got lower melting points, so this will be the answer. Okay, if you see the third option also, refractory alloys have got higher melting point, so this cannot be used. Okay, if you see the last option, large freezing range alloy, means alloys which has got freezing range, which has got higher freezing range, that is delta T, which has got higher freezing range, and where solidus and liquidus lines are present. So this will also not serve our purpose. Okay. The third question in manufacturing is, a plate of thickness H equal to 120 mm is cold rolled in a mill with a roll diameter of 200 mm. If the coefficient of friction mu is 0.1, the maximum possible reduction delta H in a single pass is. We have to answer in one decimal place. So here, since rolling is taking place and the radius of this roll is, here it is given 200 millimeter, which is dia, so divided by 2 is equal to 100 mm, and this plate has got thickness of 120 mm, and there is a reduction, so this will H1, and if you suppose this one, then H1 minus H2, is basically reduction, and we know that delta H, that is the reduction, is equal to mu square R. Delta H max means maximum reduction in a single path. So we need to use this formula. So according to this formula, mu we have been given here 0.1. If you take a square into 100, that is 0.01 into 100, that is 1 mm. So 1 mm will be the answer. Okay. Now the fourth question is, which of the following welding processes is not suitable for joining thin metal sheets? Here we have to join thin metal sheets. So in thin metal sheets we can use, you have to remember here, we can use gas metal arc welding, we can use it. Okay, we can use electron beam welding also. In electron beam welding, basically fast moving electrons are allowed to hit on this surface. So because of this, high energy is produced. Laser beam welding, in laser beam welding, laser is passed and it is allowed to melt it. But in the case of electroslag welding, which is a special process in which we join very thick material, very thick plates, basically very thick plate is joined here. So this electroslag welding will not be used for joining thin metal. So this will be your answer. Fifth question is, a long oil pipeline made of steel is suspected to have developed a scale on the inner surface due to corrosion. Which of the following non-destructive techniques is the most suitable for detecting and quantifying such a defect? So here it is given that this is a oil pipe and in the inner surface corrosion has taken place and which has formed scale. Now just because of this formation of a scale, the thickness, the overall thickness of this pipe will increase. So how can we detect this increase in thickness? So we can detect increase in thickness by method which I will discuss. So now let us go option by option. If we see dye penetrant test, dye penetrant test is used for only surface defects. So here, since it is a pipe, oil pipe, so since corrosion is taking place in the inside, not on the surface, so this method will not be used. Magnetic particle inspection, magnetic particle inspection is also done for surface defects, top surface defects. So this will also be not used. If you see acoustic emission method is basically used to detect the propagation of crack, so here even if there is a crack on the surface, so we need to use acoustic emission if there is a movement of crack and we want to measure the crack. But since here corrosion has taken place, so we need to just measure the thickness, like what is the thickness it has got. So this method is also not valid. Ultrasonic inspection is valid because in ultrasonic inspection we can also measure the thickness of the sample. Suppose this is the sample which is tested. So here ultrasound moves through this and reflects back. So this is the time which takes for its travel, and according to this we can also measure the distance, that is the x. So ultrasonic inspection is also used to measure the thickness of a material, and since here due to corrosion thickness will increase, so with the help of ultrasonic inspection we can detect, like the thickness of this pipe has increased and we can say that corrosion has taken place in the inside. Now coming to sixth question. Consider the following engineering components. First one is gas turbine blades, tungsten based heavy alloy penetrators, self lubricating bearings, engine block of an automobile. Which of the following two components are produced by powder metallurgy? So question is about powder metallurgy. So in powder metallurgy we produce powder and we compact it and then sinter it. If you see gas turbine blades are generally not produced by this powder technique. It is produced by simple casting mechanism and also single grain casting, it is called basically, or single crystal. Now tungsten based heavy alloy penetration. Yeah, tungsten based material are generally produced by powder metallurgy because tungsten has got melting point which is very high, and hence we are not able to do casting and after that machining and everything. So we use in the form of powder and we make it. Self lubricating bearing. Self lubricating bearings are also produced by powder metallurgy because in self lubricating bearing, this is a special type of bearing in which we use two different types of particles, like you see here. Suppose this is the bearing part, and we also add some copper particles here, or copper powder. So what happens when high temperature is reached, or due to friction, the lower melting, maybe here copper is, suppose copper is present, then copper will try to melt and it will provide lubrication. So that's why this is called a self lubricating. Means there is no any external need of oil. So self lubricating bearing are produced through this method. Engine block and engine block is generally produced by casting only. So Q and R. So Q and R is here. So option B is correct. Seventh question in manufacturing is match the manufacturing processes in group 1 with the types of cracks in group 2. So arc welding, extrusion, drawing, rolling, and the cracks are edge crack, chevron crack, surface crack, liquefaction crack. So we will try to match it. Then first, if we see arc welding, so arc welding, some liquid phenomenon is taking place during arc welding. So generally in the case of arc welding, what kind of crack it can take place? Edge crack? No. Chevron crack? No. Surface crack? Surface crack, it may, but liquefaction crack is more favorable because it is related to welding. During welding, high temperature is reached, and it can happen that the material, some other elements can melt, and this can lead to liquefaction crack. So P should match with 4. Okay. In extrusion basically chevron crack occurs and surface crack also occurs. So just hold it for a second. Now let us check to drawing part. In drawing, chevron crack also occurs and surface crack also occurs. Okay, now coming to rolling. In rolling, edge crack occurs. There is no chevron crack, but surface crack can occur, but generally it does not occur. But as edge crack is definitely that it will pertain to rolling. Now, so here P matches with 4 and S matches with 1. So P4 and S1, P4 and S1. Okay, P4 and S1. Okay, so this is here. So Q matches with 3 and drawing matches with 2. Now, so here I have gone through the options only, but if you try to analyze, then in the case of extrusion, surface crack is more prominent, and in the case of drawing, severn crack is more prominent. Like, maximum chances are there that in drawing process severn crack will occur. Severn crack occurs in the middle part during drawing, and surface crack on the surface. So in drawing, maximum chances are there that severn cracks occur. That's why R matches with 2 here. And in extrusion, surface crack chances are more. That's why it has matched here. Okay. Now, the 8th question is, the ideal plastic work involved in extruding a cylindrical billet of length 100 millimeter. Billet has got length of 100 millimeter from an initial dia of 20 mm to a final dia of 16 mm. Okay, so initially it has got dia of 20 mm. Suppose after this extrusion process we have converted into 10 mm and length will be something, so let it be. So from 20 D1 to D2, from 20 to 10, the flow stress in compression is 40 MPa. So flow stress is 40 MPa. Now we have to calculate the energy required. So we know that energy per unit volume required is stress into strain. Okay, so here stress is constant, which is equal to 40 MPa, and strain is basically ln R. So 40 into 10 power 6 into ln R, that is 20 square by 16 square. Okay, you got this? Now, from where we have got this formula, so I want to tell about this formula. Here it is given that it is ideal plastic work. Means ideally, this is the plasticity which is taking place at 40 MPa constant, and this is the strain, and this is the strain, and strain, suppose let it be ln R. So area under this curve will give you energy per unit volume. Okay, now since here the question has been asked in joule, that is the total energy, so you have to multiply it with volume also. So total energy equal to 40 into 10 power 6 ln 20 square by 16 square into, what is the volume of this billet? That is pi r square h equal to, let me write, pi r is here 10 square into h, that is 100. So if you calculate this, then your answer will be 560.53 joule. So your answer is this. Okay. And the last question of manufacturing is, during upset forging and considering friction, which of the following profiles represent the axial compressive stress? In this profile, the absolute value of compressive stress is plotted on the y-axis. So suppose this is your job and we are compressing here, or we are doing upsetting with the help of hammer. Suppose this is your hammer, and we have to assume that there is a friction. So whenever there will be a friction, so what it will happen, that there will be friction, more friction at this junction as compared to the friction just near. Okay, so, and since load will be distributed from this center, so maximum load will be at the center, and after this load will decrease. Okay, load will decrease, and hence at the center maximum deformation will take place. Means maximum deformation, maximum upsetting will take place, and at the end of a lower deformation will take place. That means the compressive stress at the middle part will be maximum, and in the lower part, in the side part, in the edge part, it will be low. So which curve represent this? Like if you plot compressive stress, then it will be higher, then it will be lower, then lower. Okay, it is like this. So this curve basically represents this condition. So correct answer will be P. This is the last question. The temperature profile, temperature in Kelvin of an arc weld across its weld is given as T is equal to 2000 exponential minus 0.3 x square, where x is in mm. Is the distance from the weld center. The melting point of the base material is 1500 K. The width of the fusion zone E. Here the temperature distribution is given using this expression. So this expression will somewhat be like, you see, from 2000 Kelvin, if you take here x equal to 0, then it will be 2000. So from 2000 the temperature will vary like this in the both side, and the point where the temperature will be equal to melting point, suppose let it be this point. So this region, that is length, width of weld. So now here the expression is given minus 0.3 x square. So let us find where this function has got the value of, which is equal to melting point, and this melting point is 1500 Kelvin. Okay, so let us put this value. So 1500 is equal to 2000 minus 0.3 x square. So after solving this, you will get x equal to 0.979. So this x is basically this length, because x is given here that it varies from the center. So x, this x, but we have to find this x also, because it is a symmetrical function, and the width will be this one. So width will be equal to 2x equal to 2 into 0.979, that is equal to 1.958 mm. Okay, so in this question basically it was asked the width, and here we have to calculate first x at which 1500 Kelvin is met, and after that we have to multiply it, because total width of this weld zone will be twice of the value x. Okay, so hope this will help you. Thank you.